I'm going to demonstrate this construction staging with the help of a case study, with the help of a bridge that I'm currently working on in the Monastery We Upgrade project. And this is a 3-span continuous bridge with the precast Super-T girders, which are simply supported in while erection, like when and then they're continuous after the deck pour and after the continuity pour is hardened. So the construction sequence is you first place the Super-T girders on temporary supports, and then you pour the deck concrete on the simply supported girders without pouring the deck concrete on the continuity portion. And then once the concrete deck is set, then you pour the continuity deck pour, and therefore from this construction sequence, you can say that the girders are simply supported for the dead load of the girders and the wet load of the concrete deck pour. But when the concrete continuity pour is activated, it becomes continuous, and then when you place the load of the crash barrier and the wearing course, it becomes continuous. It acts, there's hogging moment at the supports, and when there is live load, there is hogging moment at the supports. So for simulating this in space, guys, you need more than one model to have one model where the boundary conditions are simply supported, and then a different model for a case where the girders are continuous for live loads, and also simulating the behavior of a plain girder and then converting it into a composite girder where the section properties change and the stress analysis changes. All this takes more than one model, which I felt to be time taking in space gas. I can say that you can do whatever you're doing in Midas in space gas, but would definitely take more effort and more time compared to what it takes in Midas. So this is the structure that I'm working on. So this is a 3D extruded view in Midas. So for creating a construction stage, you first need to create structure groups, boundary groups, and load groups to activate each of them at in a particular stage. I'll give you a description of the structure. So it's a 3-span continuous bridge with a maximum span of 30 meters. The spans on either side are around 20 meters, and the substructure is a portal pier in the portal piers with a group piles, and at the abutments, it's a normal arrangement with 2 rows of piles. So I've classified the members as longitudinal members with all the longitudinal members, but which can again be divided into 2. The longitudinal members which would be activated in stage 1, and then the longitudinal diaphragm members, that is the solid part of the diaphragm, which is activated when you pour the continuity pour. And then there's the transverse members which are activated once the deck pour is set, and when it's hardened, it's basically distributing the loads to the longitudinal members. Then you have the supports, the piers, the dummy elements which are just forming the boundary. You'll have a better idea of it once I show it in the model. Yeah, I'll also show you the how we create an arbitrary section using the section property calculator in Midas, and how the non-composite section is converted to a composite section using the composite sections tool, and then how we set up the construction stages. So in stage 1, we'll just activate the longitudinal girders, the plain Super-T girders, and with boundary conditions with only temporary supports, which would be removed later once we have a single row of bearings set above the pier, and then we're just activating the dead load of concrete in this stage. And in stage 2, we're pouring the deck pour. So it's still simply supported, but and the property of the section is still just bare Super-T girder, and the loading is just the wet concrete of the concrete. in stage 3, once so the duration of the stage 2 is 14 days. That is, we are allowing 14 days for the composite action to get activated. And once the composite action is activated, we are activating the transverse members and the diaphragm members and the continuity portion where the girder becomes continuous, a 3-span continuous girder from a simply supported girder. Stage 4, we are just deactivating the temporary supports and adding the wearing course and the crash barrier load. And then stage 5, this is just to capture the time-dependent effects. You usually give the duration of the stage 5 as 100 years, which is 365,000 days, just to capture the creep and shrinkage effects or the time-dependent effects. Yeah, so this is the activation of the composite section. So a composite section is a combination of sections 1 and 2. 1 is the bare Super-T girder, and 2 is the concrete deck. And we need to activate the composite girder in stage 3. So I've defined the composite section, composite stage as S2 surfacing, which is stage 3. We'll do a demonstration of it next. Let me open our, this is a final analyze model. Let me just open our demonstration model for you so that I can do it all over again. Let's have a look at each of the groups. This is the longitudinal members in the grillage. Which are again classified into two, divided into two, the longitudinal stage 1 girders and the longitudinal diaphragm members, which are activated in stage 3. These are the transverse members, that is, they have a property of the deck thickness. In this case, it's 180 mm with width of the equal to spacing of the grillage, and the dummy members, which form the boundary of the boundary of the bridge. These are the permanent supports. I've included all the superstructure as piers because I'm activating all of it in just one stage at the beginning. These 4 groups are for settlement, for activating the settlement settlement analysis. So let's recreate these stages. So stage 1 is just for 1 day, and we're activating the piers first. We have to give the age of the members if we want to include any time dependent effects to it, but because we don't include any time dependent effect for the substructure and the transverse members, you don't have, it's okay if you don't specify the age of the members that you're activating. But for longitudinal members, by the time they're being placed on the temporary supports, if the age of the girders is around 30 days, you can just activate it so that it doesn't take into account the creep, the shrinkage strains till the age of 30 and the creep effects till the age of 30. It just excludes the strain values till the age of 30 because it's free to expand a contract in that period. And the piers, the longitudinal members, and the temporary supports. The age V0 just modified, and the boundary conditions just activate the temporary and the pier support. The pier supports include the the pile springs and the supports at the bottom of the pile. I think I better show this to you. After this, and in loads, just activate DC, which has the self weight. Okay, I better show you the boundary conditions and the load groups. So the boundary condition, the load groups, the DC has the self weight of the concrete, just the self weight of the Super-T girders, and PT has the pre-tensioning strands, the pre-tensioning effects. The deck has the deck load group has the wet concrete loading on it. SIDL is the wearing course, and barrier is the because there's a shortage of time. We can't really model all the loads in. We can't really model it from scratch and apply all the loads. So I already have a model, and I'm showing you the basic tools that we that I think are present in Midas, and which are not present in Spacecast. So yeah, and the temporary supports. We have 2 rows of bearings because it is simply supported. For temporary supports and permanent supports, we just have 1 row of bearings. You have a rigid link connecting the top of the girder to the bottom of the girder. To give you a better view, just activate the nodes. The top of the girder is connected to the bottom of the girder with a rigid link, implying that the section is rigid. That the plane strains remain, the plane section remains plane concept, and after that you have the elastic link which connects the top of bottom of the soffit of the girder to the bottom of the which is actually simulating a bearing. You can give this shear stiffness and the vertical stiffness of the bearings to this elastomeric bearing, and then a rigid link connecting the top of the pier cap to the center. So now that you have a better idea of what load groups and what boundary groups are defined. So in stage 1, we're activating the piers, the longitudinal members, and the temporary supports. And for boundary conditions, we're activating the temporary support boundary conditions and the pier support boundary conditions. And in loads, we're activating just the self weight of the girders. In stage 2, have a duration of 14 days just to allow the concrete to harden, and we just have to activate the deck load on it, and nothing else. We're not activating any elements or boundaries in this boundary condition in this. And okay, stage 3. In stage 3, the concrete hardens and the section becomes composite, and all the transverse elements are activated, and the continuity behavior of the girder is activated. So let's activate the transverse members first, and then the diaphragm longitudinal members, then the permanent supports, the dummy elements which are just forming the boundary of the bridge, and the diaphragm. All the other members have been activated before, or needs to be activated in the next stage. The boundary condition, just activate the permanent supports. And in load, we are not activating any loads right now. Okay. Stage 4, in this stage, we are deactivating the temporary supports and adding the crash barrier load and the deck load and the bearing course load. So there's no element that we have to activate. In boundary conditions, we need to deactivate. So there's a tab here, there's a window here where we can deactivate a set of bearings. So just deactivate the temporary bearings here, temporary supports, and in load, activate the barrier load first and the SIDL load next. So so to give you an idea of a better idea of how we are activating the loads, you can do it in steps over the duration of the stage. If the duration of the stage is 14 days, you can add steps within the 14 days, like a step on day 1, a step on day 2, a step on day 3, and a step on day 4, and you can choose to activate a particular load on any day. Like for the barrier, you can activate it on the first day, and you can activate the SIDL on the second day. This is more useful if you are activating post-tension tendons one after the other. You can activate the if you have to capture the elastic shortening losses, which are cumulative. You can activate the tendons as per the requirement or how it is done on the site, just to cumulatively add the effects of the previous tendons, effects of elastic shortening. So in this case, I'm just activating both of them on the same day. Stage 4, yeah, that's it. And stage 5, like I just mentioned, it's just to capture the time-dependent effects for over a period of 36500 days, which is 100 years. Okay, in stage 5, you can have 30 days, 1 month, 365 days, 1000 days, just to get what the creep in, just to get an idea of how much the structure is undergoing shrinkage strains and creep strains at these particular life, this particular age of the structure. Okay. Yeah. So once this is done, we also need to create. So before doing this, we have to create a section. A section using the section parameter. This is showing a I girder, but we'll create a Super-T girder. Using the section property calculator. I think it's taking some time to react. Yeah. So select the units. So basically we are importing a section from the AutoCAD file, from the DXF file, and if the AutoCAD file is units in mm, you can choose units in mm, or if it's in meters, then go for meters, or whichever units it is in, based on the comfort of the user, and import the DXF file. It's got a lot of other sections here as well. So this is the particular section that we're using for this bridge. Section, in model, go for section and generate, and plane, because this is a plane and not a line. Calculate section properties. Just select the whole section and apply. So it calculates all the section properties once you're doing this. And to export this into Midas, you need to go to model, section, export Midas section file and create a section here. Mid section. Click this section. Apply. Once it's done, you can just minimize this. Go to mid section. Section data, import section from SPC. Okay, and yeah, here it is. Just define these T1, T2 if you're intending to design the section in Midas, but I'm not usually designing the section in Midas. But still, just let's give an input here. Thickness is 1500. HD. Oh yeah, the width is 2000, 1500, 1500. And you can also change this offset from the center to center top. It will just create a rigid link between the CG of the section and whatever offset you're providing. Section. Okay. So this is just the bare Super-T Girder property, but you also need a mid composite section property where the deck is activated. So you have a input where you can give the properties of the slab. The width of my slab is 2000 and the thickness of the slab is 180. There's no haunch here. Usually if the deck is inclined, just to accommodate the inclination of the deck, we usually have a haunch there, but in my case there's no haunch. Super-T Girder and section 2 is the deck section, and I'm importing the section 1, which is a non-composite Super-T Girder, which is midsection, and it is activated here. Deck slab, the width of the Super-T is 2500. Yeah. Okay, the offset is center top again. And okay. Yeah. So you need to activate the composite section when the section actually becomes composite. So we are activating the girder in stage 1, which is midsection, mid composite, and is normal. And you can, so in this case, because both of them are concrete, and because while defining the composite section, we usually have to give the modular ratio here, which is the ratio of the modulus of elasticity of the one which has of the material which has higher Young's modulus, and to the material which has lower Young's modulus. In this case, because it's concrete to concrete, we are providing it as 1. But if it is steel, you can provide a modular ratio of around 6, or based on project requirements. So let's activate this. It's been activated in stage 1, mid composite, normal, and the material active stage 1. But the Super-T Girder is being activated in stage 1, but the deck is being activated in stage 3. So just provide stage 3. Provide the age is 30. This is for the time-dependent effects, and the age of concrete is 0. Just provide the nominal thickness values. This can be auto-calculated later, so you don't have to provide this. So to update the hypothetical thickness, you can go to properties and change property. Nominal size of the member, just select whichever elements you have to. We can keep this session more interactive. You can just keep posting more questions. If I keep getting any questions, I'll try to answer those while I'm doing the demonstration. So you can select the longitudinal elements and apply. It'll basically apply the section hypothetical thickness based on the calculation here, which is 2 times area by the perimeter, which is in contact with the surface. So let's get to the analyze model just to see the results. So from this, in stage 1, if you check the dead load moments, you can see that it is simply supported. In stage 2 also it is simply supported. But you can see the moment increasing from stage 1 to stage 2 because there's an extra load due to deck. It's 2130 now. And in stage 3, once the deck becomes composite, you'll see that the girder becomes continuous, not for dead load, but just for the live loads. In stage 3, it is composite. You can see the activation of in stage 4 because the crash barrier load and the wearing cores have been activated and the deck is continuous. You can see the hogging moment coming up here. And in the post processing stage, you can look at the live load moments. Yeah, you can have a look at the hogging moments for live loads. So this shows that the bridge is simply supported for permanent loads, live load for the dead loads, and continuous for the crash barrier, the wearing cores, and the live loads. You can also check the stresses. Stage 1. Part 1 is the bare Super-T girder. Check the dead load stresses at the bottom. If it is a composite section, you always have to choose if it is part 1 or part 2. And if it's not a composite section, then you can just go for total and select at what fiber you need the stress. It can be the top fibers are 1 and 2, and the bottom fibers are 3 and 4. So this stress calculation is based on the section modulus of a bed Super-T girder, but once it comes to stage 3, the stress calculations are based on a composite section. Yeah, so that's about construction staging. But if there's any question on construction staging, please keep it coming. I can show you some particular effects that we're trying to simulate here. Okay, if there's no question, yeah, maybe I'll just move to the next tool, which is the creep and shrinkage calculator. The creep and shrinkage are time-dependent effects, and we're trying to. This is one very good advantage when we are using Midas, because it also brings in a different a parameter which is not available in SpaceGet, which is time. So for creep and shrinkage, what it actually does is it calculates the strain as per the codal requirements, be it CEV, FIP, or ASTO, or in our case, AS5100. So we are the ones who are providing the input parameters like the grade of concrete, the exposure environment, which is defined as arid, interior, temperate, or tropical in AS, but in other code it's usually in terms of the relative humidity. Then the hypothetical thickness, which is a member property and less to do with the material property, and the drying basic shrinkage. This is based on the location of the project and the age of concrete at the beginning of the shrinkage. All these parameters are defined by us, and then these inputs are used to generate a shrinkage strain to time curve and a creep coefficient to time curve, which it uses later on in the construction staging to get the strains, to induce the strains. So creep and shrinkage are induces strains in the model. So it applies an internal force which induces a and this deformation when restrained by supports or boundary conditions in the model creates secondary effects. So I'll explain it to you properly while I'm doing it in Midas. So this is the calculation that it does based on this is just a calculation from the AS5100 code, which where it adds up the chemical shrinkage strain and the drying shrinkage strain. This is the calculation for the creep coefficient based on time. Well, let's get to the model. This is the window where you define the time-dependent material properties for creeping shrinkage. You can choose the code here. You have a lot of options. We're going for the 2017 code. The age of the compressive strength of concrete is 50 MPa. And the exposure classification for Melbourne is tropical near coastal, and the hypothetical thickness, you can just enter any value here, but it would be overwritten by a value that we are providing using the change element properties window. And the drying basic shrinkage is an input based on the location, which is 900 micro strain for Melbourne. And the age of concrete at loading is 3. You can change it based on the project to 30. And once the time dependent property inputs are defined, you can get the shrinkage strain to time curve, you can choose to give the start date and the end date, the number of steps. I think we're running out of time, so I'll just speed up the whole demonstration thing. Yeah, once the creep and shrinkage properties are defined, you just have to link it to the particular element that we are looking to capture the effects of creep and shrinkage. In our case, in the grillage, we are only looking at the creep and shrinkage of the longitudinal girders because we don't want any creep and shrinkage effects of the transfers, which would create a complexity in the grillage and in plane forces. So it's just a longitudinal elements. So let's the longitudinal material properties are C50. So just link it to this over here. The creep parameters and the compressive strength parameters. This is not really required at this moment, but the creep and shrinkage parameters, you can link it to it. To the material and add or modify. It's already been created to get the results in the model. Let's see the strains in stage 1. So you only get deformations for creep and shrinkage primary, which is the applied deformation. Let's just check shrinkage. In stage 1, let's check in millimeters. In stage 1, first step, there's not a lot of shrinkage. When you come to stage 2, also there is not a lot of shrinkage, but once you come to stage 5, let's just check dx. Shrinkage is a parameter which is not dependent on the applied loading. It's just it's just a function of the atmosphere, the environmental conditions, and the section properties. So at the end of stage 5, you can expect a shrinkage of 5 mm for the structure, which is being induced in this. And this deformation is causing secondary effects, which can be checked in forces. This creep secondary. Shrinkage strain induced in the model is creating these effects into the girder and the substructure. If you look at the load cases, you can see that the dead load, the creep shrinkage, and the secondary shrinkage secondary, and then summation. A summation is an addition of these the forces, the loads that are above it, but which does not include the creep primary and the shrinkage primary, because they are internal forces which are induced to get the deformation. This is the same case for temperature gradient creep and shrinkage effects, but in case of prestressing, it is an applied loading which is inducing deformation. So you also have to take into account the primary effects of prestressing. So this is about creep and shrinkage, but and I'll just give you a. It's 12:47 already. I'll just give you a quick demonstration of prestressing. Yeah. So for prestressing, you first need to create the material properties and then the tendon properties based on what we're taking for the project. If it is a pre-tensioned girder, then you get to choose if it is pre-tension, because you don't have certain losses for a pre-tension girder like the anchorage strip loss or the wobble loss or the friction loss. But if it is a post-tension girder, then all these inputs would be activated. The coefficient, the curvature friction factor, the wobble factor, and the anchorage slip, if it is 6 mm or what based on the pre-stressing instruments that we're using. And then you need to define the strand profile. And apply the pre-stressing load. If it is a pre-tension girder, you can just apply the stress at the beginning and at the end of the strand. But if it is a post-tension girder, you can choose to apply loads only at the start or at the end based on how you're doing it on the site. And the pre-stressing tool also gives us the losses, which I think is very which has been really useful for me when I was working on some post-tension girder bridges. Yeah, I'll give you a demonstration of. This is where you define. I'm just trying to open an unanalyzed model to show you to demonstrate how to create a tendon profile. In the meantime, I really found this pre-stressing application in Midas very useful to calculate the secondary effects, which are very difficult if you're doing it on space gas. In the meantime, I can take some questions from you if someone's having any questions. Yeah, in composite section, do you give density to slab sections? Yeah, if it in composite sections, we do not have to give a density to the slab sections because we are applying it as a UDL on the girders. So if you're giving it a density equal to density of concrete, again, it will be a duplication of loads. So just be careful so that you don't give the density of concrete deck. Just give it to 0. The member properties input. How do you input eccentric deck width in composite section? Sorry, this question is not clear. So I think there's a problem with I'm going to reopen the model, but I can answer some of the questions here. So when you run live loads post construction stage, is it run on 365 days old model? In that case, long-term section properties would be used for, yeah. So when you run a live load, it's not based on the construction stage model. It is based on the final model, which is independent of what construction staging we are trying to simulate. The construction effects are only for the permanent loads. So that is still whatever loads you're activating in the construction stages. So you do not have to activate the live loads for during the construction stages. So why is that? Because we're trying to simulate the effects of creep and shrinkage, and for creep and shrinkage, it's just the permanent loads that you require. So we do not have to activate the live loads on it. So it's not based on the long-term properties. All the transient effects like the wind, the live loads, and all of that, they are based on the short-term section properties of the composite section. Bridge is continuous only with deck slab or composite section. Bridges continues only with deck slab or composite section. Sorry, Valentino. Figurado, I'm not. This question is not clear. If you can just post the question again, I'll try to answer it. How does the soil spring in Midas vary from space gas in terms of pile spacing? The application of the soil spring is very similar because we are doing the calculation and inputting the soil spring stiffness. But if it is a plate, and if you can just provide a I'll just give you a demonstration of it. Boundary. If it is a surface spring, you can just select the surface and apply the springs, and it will calculate the equivalent area which is available on the plate and apply an equivalent spring stiffness to it based on the area. How is it different from space gas? The lateral springs are not different from what space gas offers. It is the compression only springs which are not available in space gas, and the surface springs. I'm not really sure if the surface springs are available in space gas. What are pre-stress secondary effects? Yeah, so pre-stress secondary effects are so I'll just try to explain you how the pre-stressing is working. So when you give a pre-stressing load, you're applying a tendon with some eccentricity, and you're inputting an axial load onto it. You're stressing it, and when that is done, it at a particular section, it is the axial load and the moment which is caused due to the axial load, which is eccentric to the centroid of the section, and it tries to deform the whole girder. If it is continuous, it tries to deform the whole girder in the shape of the applied pre-stressing loading. But when there are supports, when you have supports on a continuous girder, they're trying to restrain the deformation of the girder, which induce reactions into the supports, and these reactions in turn cause secondary forces on the girders. So that is, I hope I'm making it clear, but you can still come back to me after the session if you still are not clear with the pre-stress secondary effects. How do you compare Midas with Autodesk for bridge design? Is it a structural bridge design software? So I think I really wouldn't say that. I can actually say that Midas is very efficient and more it does more stuff than what Midas Autodesk structural bridge design software can do. Are there more questions? Yeah. I'll try to show the pre-stressing tool before we can just close it off. And the MCT shell command as well. So because I don't have the unanalyzed model, maybe I'll just show the analysis results of pre-stressing. So this is the effect of tendon primary, and secondary effects of pre-stressing are only induced if it is a continuous structure. But if it is a simply supported structure, because there's no restraint to the deformations caused by pre-stressing, there are no reactions generated in the supports, and therefore there are no secondary effects due to pre-stressing. So in this case, because it's a simply supported, this is a simply supported bridge in Melbourne, and therefore we don't have any secondary effects. You can see tendon secondary would be minimal if you look at the values. It's just 37. That's because of the internal restraints which the transverse elements create. The tendon primary, which is like 6,000. Let's have a look at the stresses induced due to dead loads at the bottom fiber. The stresses induced in the bottom fiber is 11.22 MPa, but the stresses induced due to tendon primary and the bottom fiber is compression, which is 40. So when it comes to a summation of all the tendon dead loads and the creep and shrinkage effects, the summation at the bottom fiber would be 33 MPa. So there's still a decompression of 33 MPa. And when you add the live loads in the construction stage, in the service stage, at the bottom, you can see that the tension has there is tension in the bottom fiber. So it's just due to the live loads. The live loads are causing a tension of 15.4 MPa in the bottom fiber. But when it is added with the permanent effects, with the summation, which includes the pre-stressing effects, there's no tension at the bottom fiber. You can have a look at it here in SLS case. Yeah. So there is tension in the last girder. That's because it is a longer span, and maybe you'll have to increase the tendons or increase the eccentricity of tendons to get rid of the tension present in the last girder. Yeah, I think that is what I can show you for today, and because we've reached we've reached our time limit. Thanks for attending the session. If there's any other questions, you can just post it on the link here to the global technical support of Midas, or I can answer them if you can get in touch with me on any social media platform. Thanks. It was a good session. Thanks.